All right, today's lesson is the scalar equation of a line. So what's the goal? Again, it's knowledge and understanding, really. Can I take a given information and can I create a scalar equation of a plane using previous knowledge? So I want you to be able to come up with the scalar equations. So the question then is, why do we never get introduced to the scalar equation of a line in 3 space? We were shown the scalar equation in 2 space, ax plus by. This is the one I said you used extensively through the grade 10 course. Why was there no scalar equation when it came to dealing with it in 3 space? Well, I'll give you an explanation right now. Based on what we did in 2 space, we can assume the process, it should be the same. We know that the dot product of p naught p and the normal should equal a value of 0. And what should have came out of it, it should have been ax plus the by plus cz plus d equals 0. That's what we would have anticipated if I let you take a guess. But let's just sketch this out and talk about what the result, or what it actually looks like when we go ahead and do that. So creating, actually I don't know if it's really necessary to bother with the creation of a 3D axis for now. Let's talk about that. If I have a line in 3 space, all right, and we want to take p naught p, so p is a point on the line, there's point p, there's p naught, and I want to dot it with its normal. What arises, or what problems happen, is that I'll have a normal right here that's perpendicular to the line, but also I could rotate that normal around a little bit and have a normal here, a normal over here, a normal over here, a normal over here. So each of these normals, because we're in 3 space here, each normal results is still perpendicular to our line, and in 2 space there's only one possible, because it's on a piece of paper. It's either going to be going up or down. So this is your 3 space. So we're able to find an infinite number of normals. If I just add a little bit more room here, if we were only looking at it in terms of 2 space, so the piece of paper, so in 2 space, our normal would either go this direction or this direction, because it's as drawn on the page, and those are really the same normals, just opposite directions, so they're the negative of each other. However, in 3 space, because you end up with an infinite number of normals, there's not just one normal to deal with when you're doing the dot product. What's the result? I already mentioned that we have an infinite number of normals. Infinite number of normals. So what that then means is that if you lie an infinite number of lines side by side, they create a plane. So therefore, the normals will form a plane. Okay, so all those normals, if I keep drawing them on and I keep filling in the space, what happens is you end up with maybe a circle, but it extends in all directions, and all those red arrows start forming their own plane. So therefore, in 3 space, we take the dot product of p naught p with its normal equal to 0. The result is the plane ax plus by plus cz plus d equals 0, where our normal is equal to ABC. Okay? So there's the explanation. Here is the formula. for the scalar equation of a line in 3 space. So, summary. With the summary here, let's just quickly talk about, we're going to make a chart here. So vector form, parametric, parametric, symmetric, and standard. And in my first column, we'll talk about the 2D line. So what forms exist for a 2D line? I can write it in vector form, I can write it in parametric form, I can write it in symmetric, and I can write it in standard. So all 4 forms exist for a 2D line. If we're dealing with a 3D line, well, I have a vector form for a 3D line, vector form for a parametric, symmetric form of a 3D line, but no standard form exists for a line in 3 space. And finally, planes. We already talked about it yesterday. Vector form, it has a parametric, it has no symmetric form, but it does have a standard form. So it is important to know, because if you are asked to find the symmetric form of a plane or a standard form of a 3D line, you're not wasting your time going through calculations when you know the answer already, and the fact that it just doesn't exist. So an example, develop a scalar equation of the plane through that point, normal to that. So there are the 2 methods, so I'll quickly go through the methods. P naught P dot the normal equals 0. So P naught P is x minus 4. So you're just taking point P, which is x, y, z, some point on the plane, and it'll be minus the point given, minus point P, y plus 1, and z minus 3, dot the normal, and the normal is given. So 3, 5, and 2 is equal to 0. So we end up with 3 x minus 4 times x minus 4 plus 5 y plus 1 plus 2 z minus 3 equals 0. Distribution law, collecting like terms. 5y plus 5, 2z minus 6 equals 0. So I end up with 3x plus 5y plus 2z equals, and I've got negative 12, and that's going to be a negative 1, so negative 13, so positive 13. So there's my final answer using method number 1. And again, it doesn't matter to me which method you use, I'm just demonstrating both for example purposes. So the other one is just jumping to this form and solving for your constant, your d value. So we end up with 3 multiplied by 4, so using the point and the normal here. From the normal, we have 5 times negative 1, and 2 times 3 plus d equals 0. So 12, negative 5 plus 6 plus d equals 0. D is equal to negative 13. So therefore, you would end up with 3x plus 5y plus 2z minus 13 equals 0. Same equation as method number 1. All right. So it doesn't matter which method you choose, just be aware of one of the methods and be able to complete them. All right. Time for one quick question here. So write the equation, so in vector form, and now I'm starting to identify what am I dealing with. There's only one direction vector, so this is a 3D line. So there's only one direction vector in scalar form. So write the equation xyz in scalar form. So you're asking yourself, I'm looking at a line here, and because it's a 3D line, I know 3D lines do not exist in scalar form. So answer is very simple. A 3D line cannot be written in 3D form, or sorry, in standard form. All right, so it is a comprehension question. You need to make sure you understand what can and cannot be done when you're going through our vector processes here. Find the distance between point A to the plane given. So as an aside here, we know or recall from line in 3 space, we know it was ax plus by, or 2 space, sorry, by plus c over the square root of a squared plus b squared. Now, in 3 space, and I'm not going to go through the proof and show you because it's the exact same proof, it now works to the equation of the plane, or moves to the equation of the plane, plus d, and now you have a third component in the denominator because now we're in 3 space. So to answer their question here, ax plus by plus cz plus d over square root of a squared plus b squared plus c squared equals, so we already have the equation, and we're going to use the coordinate to fill in the missing values. So minus 8 times my y value minus the z value plus 41. That's going to be over the square root of 4 squared negative 8 squared negative 1 squared. So on top I end up with 12 plus 8 minus 1 plus 41. And in the denominator, I have 16, 64, and 1. So just finishing that off. On top, 12 plus 8, that gives me 20. 61 minus 1, so it'd be 60 on top. It's already positive. And on the bottom, I would have 70, 80, 81. All right, 16, 0, 80, 81, root 81. So that's 60 over 9 units, and you can reduce that to 20 over 3 units. So that would be the distance from a point on my that given point and the plane itself. And there's the homework. If you have any questions, please let me know, and we'll get them cleared up. Good luck.